All right, so now it is time to create our first convolutional neural network. Now we're going to be using Keras to do this, and we're also going to be using the CIFAR image dataset that contains 60,000 images of 10 different classes of everyday objects. Now these images are 32 by 32, which essentially means they are blurs, and they are colorful. Now, I just want to emphasize as we get into this that the reason I'm not typing all of these lines out and that I just have them in here already is because this is likely what you guys will be using or doing when you actually make your own models. Chances are that you are not going to sit, unless you're a pro at TensorFlow, and I am not even there yet either with my knowledge of it, and have all of the lines memorized and not have to go reference the syntax. So the point is here, so long as you can understand why this works and what these lines are doing, you're going to be fine. You don't need to memorize them, and I have not memorized them, and I don't. I look up the documentation, I copy and paste what I need, I alter them, I write a little bit of my own code, but that's kind of what you're going to end up doing, so that's what I'm doing here. So this is the image dataset. We have truck, horse, ship, airplane, just some everyday regular objects. There is 60,000 images, as we said, and 6,000 images of each class. So we don't have too many images of just one specific class. So we'll start by importing our modules. So TensorFlow, we're going to import TensorFlow.keras. We're going to use the dataset built into Keras for this. So that's the CIFAR image dataset, which you can actually look at just by clicking at this. It'll bring you and give the information about the dataset. Although we don't need that right now because I already know the information about it. And now we're just going to load our images in. So again, this stuff, the way this works is you're going to say datasets.cifar10.load data. Now this loads it in as like a very strange TensorFlow object that's like a dataset object. So this is different from what we've used before, where some of our objects have actually been like in NumPy arrays where we can look at them better. This is not going to be in that, so just something to keep in mind here. And we're going to normalize this data into train images and test images by just dividing both of them by 255. Now again, we're doing that because we want to make sure that our values are between 0 and 1, because that's just a lot better to work with in our neural networks rather than large integer values. It just causes, some things to mess up sometimes. Now class names, we're just going to define a list here so we have all the class names, so that 0 represents airplane, 1 automobile so far until truck. We'll run that block of code here. We'll download this data set, although I don't think it takes that long to do that. So, okay, so wait, I guess that's good. I think we're okay there. And now let's just have a look at actually some of the images here by running this script. So we can see this is a truck. I can change the image index to be 2. We can see this is another truck. Let's go to say 6. We get a bird. And you can see these are really blurry, but that's fine for this example. We're just trying to get something that works all right. Okay, so that's a horse. You get the point. All right, so now CNN architecture. So essentially, we've already talked about how a convolutional neural network works. We haven't talked about the architecture and how we actually make one. Essentially, what we do is we stack a bunch of convolutional layers and max pooling, min pooling, or average pooling layers together in something like this, right? So after each convolutional layer, we have a max pooling layer, some kind of pooling layer typically to reduce the dimensionality, although you don't need that. You could just go straight into 3 convolutional layers. And on our first layer, what we do is we define the amount of filters, just like here. We define the sample size, so how big are those filters. An activation function, which essentially means after we apply that, dot product operation that we talked about, we'll apply rectifier linear unit to that and then put that in the output feature map. Again, we've talked about activations functions before, so I won't go too far into depth with them. And then we define the input shape, which essentially means what can we expect in this first layer? Well, 32 by 32 by 3. These ones, we don't need to do that because they're going to figure out what that is based on the input from the previous layer. All right, so these are just a breakdown of the layers. The convolution or the max pooling layers here, 2 by 2 essentially means that what we're going to do is we're going to have a 2 by 2 sample size with actually a stride of 2. Again, the whole point of this is to actually divide or, shrink it by a factor of 2, how large each of these layers are. All right, so now let's have a summary. It's already printed out here. We can see that we have, oh, wait, is this correct? Mobile net v2. I don't think that's correct. That's because I haven't run this one. My apologies on that, guys. This is from something later in the tutorial. We can see that we have conv2d as our first layer. This is the output shape of that layer. Notice that it is not 32 by 32 by 32. It is 30 by 30 by 32 because when we do that sampling without padding, right, that's what we're going to get. We're going to get 2 pixels less because the amount of samples we can take. All right. Next, we have the max pooling 2D layer. So this now says the output shape is 15 by 15 by 32. which means we've shrunk this shape by a factor of 2. We do a convolution on this, which means that now we get 13, 13, and we're doing 64 because we're going to take 64 filters this time. And then a max pooling again, we go 6 by 6 by 64 because we're going to divide this again by a factor of 2. Notice that it just rounded, right? And then conv2d, so another layer here, we get 4 by 4 by 64, again, because of the way we take those values. So this is what we've defined so far, but this is not the end of our convolutional neural network. In fact, this doesn't really mean much to us, right? This just tells us about the presence of specific features as we've gone through this convolution base, which is what this is called, the stack of convolution and max pooling layers. So what we actually need to do is now pass this information into some kind of dense layer classifier, which is actually going to take this pixel data that we've kind of calculated and found, so the almost extraction of features that exist in the image, and tell us which combination of these features map to either, what one of these 10 classes are. So that's kind of the point. You do this convolution base, which extracts all of the features out of your image, and then you use the dense network to say, okay, well, if these combination of features exist, then that means this image is this, otherwise it's this and that, and so on. So that's what we're doing here. All right, so let's say adding the dense layers. So to add the dense layers is pretty easy. Model.add is just how we add them, right? So we're going to flatten all of those pixels, which essentially means take the 4 by 4 by 64 and just put those all into a straight line like we've done before, so just one dimensional. Then we're going to have a 64 neuron dense layer that connects all of those things to it with an activation function of rectifier linear unit. Then our output layer of a dense layer with 10 neurons, obviously 10 because that's the amount of classes we have for this problem. So let's run this here. We'll add those layers. Let's look at a summary and see how things have changed now. So we go from 4 by 4 by 64 to 1024. Notice that that is precisely the calculation of 4 times 4 times 64. That's how we get that number here. Then we have a dense layer and another dense layer, and this is our output layer. Finally, this is what we're getting, is we're going to get 10 neurons out, so essentially just a list of values, and that's how we can determine which class is predicted. So this up to here is the convolutional base. This is what we call the classifier, and they work together to essentially extract the features and then look at the features and predict the actual object or whatever it is, the class. All right, so that's how that works. Now it's time to train. Again, we'll go through this quickly. I believe I've already trained this. This takes a long time to train, so I'm actually going to reduce the epochs here to just be 4. I'd recommend you guys train this on higher, so like 10 if you're going to do it, but it does take a while, so for our purposes and for my time, we'll leave it a little bit shorter right now, but you should be getting about a 70% accuracy, and you can see I've trained this previously if you train it on 10 epochs, but I'm just going to train it up to 4. We'll get our 67, 68%, and that should be fine, so we'll be back once this is trained, and then we'll talk about how some of this works. Okay, so the model is finally finished training. We did about 4 epochs. You can see we got an accuracy of about 67% on the evaluation data. To quickly go over this stuff, optimizer's atom, we've talked about that before. Loss function is sparse categorical cross entropy. That one, I mean, you can read this if you want. Computes the cross entropy loss between the labels and predictions. And I'm not going to go into that, but these kind of things are things that you can look up if you really want to understand why they work. For most problems, you can just, if you want to figure out what, loss function or optimizer to use, just use the basics, like use atom, use a categorical cross entropy. If you're using a classification task, you want to do something like this. You can go up and look kind of all of the different loss functions, and it'll tell you when to use which one, and you can kind of mess with them and tweak them if you want. Now, history equals model.fit. This is just so we can access some of the statistics from this. Model.fit obviously is just training the data to this test images, test labels, and train images and train labels, where this is the validation data.